All
Okay.
right. To the first office hour of the new year, 2015.
Hey, so Happy New Year to everyone. This is Amit, and this is Alessandro here also. And hey, and we also have Santosh, who's joined us. So, hey, Santosh.
Hey, yes.
And yeah, anybody else who wants to join in the new year, just drop in and kind of ask the questions, and it'll be yeah, it'll be good to have New Year. So New Year. Oh, we've got one more. Custon's joined in.
Hi, Gustin.
Hi, Gustin. I think you can probably hear us. Hey, Gustin, just join in if you want to ask a question or say hi or anything. Anything in the new year. Anything in the new year is welcome. Hey, so I wanted to kickstart this by just it's a new year, so new year for a data scientist is it different from normal human beings, or is new year for a data scientist pretty much like the rest? I mean, I haven't done anything great in the last 2 years, other than probably other 2 days, other than think about making resolutions or think about doing something new, right? That's kind of what we do, right, in the new year. Um, so how does a data scientist look at these resolutions? Is there a way we can think about it, like quantify ourselves, or I don't know, Alessandro, have you ever tried kind of gone down this path of kind of using data science to improve yourself?
I have. So now I admit that what I've done has been pretty rudimentary, but I've definitely had a lot of thoughts on how one could take it a lot further.
Mm-hmm.
A lot of these quantified self technologies are getting pretty convenient and pretty affordable. One of the things that's kind of neat about some of them, like Fitbit, is that they have I believe they have an open API, so it's fairly easy to get data out of them, which is really great if you want to do things like compare data between, say, your Fitbit and something else.
Right.
So one of the things that I've always thought would be kind of an interesting project would be to do something like measure, use a Fitbit or something like that, measure my activity, measure, how often I exercise, and correlate it with some other factors, like every evening taking an assessment of my mood, or using the weather. I mean, this might be kind of an obvious one, but hopefully when weather's good, maybe I get out more often. Just little things like that to see. I mean, especially with things like we all know that if you exercise, that's supposed to have a positive effect on your mood. Should hopefully let you sleep better. It'd be cool to actually prove this, prove it with yourself.
So the first quantified self. I mean, we'll talk about people now do it, but the first quantified self was actually Benjamin Franklin. He used to have these 14 character virtues, and every week he'll decide to focus on one, and then he'd probably have I think he used to have a chart, and he would kind of tick whether he did successfully on it or not successfully on it. And he had this whole thing about working on that one character for a week and kind of getting that feedback loop and seeing whether it's working or not. And kind of the golden man of quantified self. Now, obviously, we have people who do much more fancy stuff with this kind of quantified self, right? I think one of the guys that we were talking earlier was this guy called Nicholas Felton, and he's been doing these quantified self reports, which he would be tracking different aspects about him for a whole year, and then he'd at the end produce a great visualization around that, right? So yeah, there we go. It's kind of like 2005 onwards, and they're good examples of both doing quantified self, and I guess also then trying to visualize it and tell kind of a narrative around it. I think both on both those aspects, those things are pretty nice. And you're right. There are many more kind of tools now to kind of make this easy for us, right? Make this easy for us.
So yeah, I mean, you know.
Yes. Sorry, go on.
So Felton definitely, you know, he takes this to a whole other level. I'm flipping through some of the things here. I'm actually not even sure what all of these are. But
Facebook messages, yes.
But
yes.
Done. Oh, everything's redacted, right? So, you know, here he's got you know, a bunch of different media that he uses. Mail, SMS, Facebook. It's kind of hard to see all of it.
Yeah, you can see the clusters, yes.
Yeah, and you see, you know, you can see how he uses different channels to, you know, different channels of communication interact with each other. You know, I mean, Feltron is definitely, or Felton, sorry, his website is Feltron, but he is Felton.
Yeah. He's the extreme of that kind of.
Yeah, and he's also very, very talented with his visualization, at least from my point of view. I don't know.
No, they're pretty good. I mean, they're a good narrator. And I think you don't have to do this, right? You can just start with some basic stuff, and you know, you can use tools also if that makes sense. But you know, one of the things about being data science is being curious. And being curious, you could be curious about yourself, and you know, so if you want to make a New Year resolution and kind of say, am I curious about what works for me, what doesn't work for me? Why don't just track it in whichever way it makes sense, and you know, like, and then kind of look at the feedback loop, and that's one of the techniques that works always. I mean, people talk about it not only. The guru of management, Peter Drucker, has a great article called Managing Oneself, and he talks about 4 techniques, and one of the technique there is kind of this feedback loop of journaling or writing or figuring out what worked and what didn't work for you in the last week. And you know, that's kind of like quantified self. You know, do something, track it, and then see whether it works or not.
So maybe we should, we have a question about QQ plots and SPLOM plots.
SPLOM plots, right.
I don't know much about SPLOM plots, but I could definitely say something about QQ plots.
Sure. Let's dive into the questions then. Yes. So Santosh, you want to elaborate? What do you want to? Can we have his mic on, Monique? I guess. Yeah.
Yeah.
Just kind of what was the what were your kind of when you looked at these plots? What were kind of your questions, and you know how?
My question was, how are they used? I mean, what information is pulled out of it? You know, from a graph perspective.
What? Okay. Only from a Q. Okay, fine. Alessandro, you wanted to take the QQ plot? That
sure. Yeah, and I guess we can. I guess either one of us can do SPLOM. Let's say okay. So QQ plots are they're a little bit. I'm going to pull up an example so I can sort of show how it works. Okay, so first I'll show this normal distribution. Let me get the screenshot back on. Screen share. Okay, so not that one. All right, so if we look here, we've got, I wonder if I can make this quicker. Yes, okay. So this is a QQ plot of a normal distribution. Okay, what does that mean? Basically what it means is a normal distribution, actually maybe I should back up a second and show a normal distribution. So this is a normal distribution. Everybody's seen this image before, or some version of it. Basically, this is how data should behave if it is if it follows certain properties, where you'll have kind of some mean somewhere, and then as you get away from the mean, the frequency drops according to this sort of S-shaped function. So you have 1 standard deviation away is has 30%, et cetera, et cetera. Now, a lot of statistical techniques basically assume that data is in this sort of distribution, and if your data do not follow this distribution, it can cause your statistical analysis to kind of go haywire. So one of the ways that you can check to see if your distribution matches this distribution is to do a GGPlot. So what you have here is on the bottom, on the x-axis, you have the theoretical quantile. Basically, if you're to do, say, 5, 100, or 1,000, random points in a normally distributed distribution, you would get something. You would get that point along that theoretical quantile. On the sample quantile, you have the actual observations. So basically, what that means is if you get 5 points, well, 5 is not very many, obviously, but you're going to have the third one is going to be right at 0. The second, and the fourth one are going to be at about like 0.5-ish, and the first and the fifth are going to be at like -1, 0.1, and 1.1, something like that. So that's where the points line up on the x-axis. On the y-axis, you have the actual data.
What is 1, 2, and 3? Are these quartiles or are they quantiles? Right, they are quantiles, or are they standard deviations?
Yeah, so this is made-up data. I'm guessing that we're dealing with a mean of 0 and a standard deviation of 1, so the 1 would be 1 standard deviation.
Right. Okay. So it's on the standard deviation on the axis. Okay.
So can it be used for multivariable analysis too, or is it generally used for applying the expected values versus the sample values?
So you can use it to check too. So first, let me finish with explaining what you do to compare it to a theoretical quantile. But yes, you definitely can compare two variables against each other as well. Although, let's see.
So one of the charts that QQ charts get when you do a linear regression. Out of the 4 charts, I think that R automatically produces. One of them is a QQ chart, which kind of looks at what the expected versus the sample would be, or expected versus the actual would be. So it does produce one of the QQ charts. So you can use it, not for multivariable. It's typically done for. I think the dependent variable, right?
You can do it. So yeah, you wouldn't do it with. Sorry, I misspoke. You wouldn't do it with 2 different variables, but what you could do it is with a different distribution. It doesn't have to be normal distribution. So, for example, if you and you could even use the distribution of one data against the other, but that's actually getting pretty esoteric. So let's forget about that. So you mostly use it just to check to see if the data line up. It's really a special case of a scatter plot. In a scatter plot, you'd compare 2 variables against each other. In this case, rather than comparing 2 variables against each other, you're comparing one variable against what that variable would look like if it were normally distributed.
Right. Yeah, that makes sense.
Yeah. So in this case, we have variables that are normally distributed, and as the n gets higher, we see it lines up much more cleanly along the line, because that's the law of large numbers and regression towards the mean. So basically, what you're going to have is, if it's perfectly normally distributed, it should lie very close to this line. If it's not, you'll see it kind of have a hump or something weird. So, like, here is an example. So where the verbal SAT is fairly normally distributed in the middle, although it kind of gets a little bit weird at the edge. And then GPA has this very non-normal
distribution.
Yeah.
Okay.
Which makes sense. So you see that for instance, this is clearly an American school because you have grade inflation. So, everybody's 3.0 or above, pretty much.
Right, very few below. Yeah, makes sense. Makes sense. Okay, so does that kind of takes QQ? What was the other one? Was Splum, right? So I think you had one on the iris plot there. So do you want to pull that up?
Sure, I can load that up. So yeah, let me get the screenshot again, the screen share again.
So Splum, in essence, is just it stands for scatterplot matrix, right? So it's basically a scatterplot matrix, which means if you have many variables, and this is a classical example in, I think, kind of clustering, right? So you're clustering iris, which is a type of flower with 3 different varieties, and they have 4 characteristics of that flower: petal width, petal length, sepal width, sepal length. So all of them are numeric characteristics. And what this scatterplot matrix does, which is what Splum means, is basically plots each of them against the other. And in this case, because both of the variables are quantitative, it just you get these different. You basically get 1, 2, 3, 4, 5, basically 6 of them, right? Because 4C2. 6 combinations, and the other side of the matrix is just kind of toggling the axis, right? So one side of the axis.
That was 4 choose 2 for those of you who, it's been a while since we've taken the screen now.
Yeah. So yes. So basically, you have six graphs and kind of the mirror image of 6 graphs, and that's what a scatterplot matrix does. Now, if you basically if you just use plot and you put any data frame in it, the basic plot function will plot all those things, and even if they're categorical versus quantitative, you'll get a scatterplot matrix. Just basic plot. It'll plot each variable against every other variable in that data frame. You can try it out on any data frame. Obviously, don't do it when there are more than 10 or 15, more than 10 variables, because you won't be able to see much. But that's what plot does, and this is what scatterplot matrices are. I mean, they are just trying to allow you to view all these variables in relation to each other one by one and see if they're a pattern. And this is a classic example where you can start to see how you could do clustering, because you can clearly see there are some characteristics on which you can separate these 3 types of flowers that are there, or 3 types of subflowers of iris that you have there, right? And I would urge everyone to basically just use plot and plot the variables in your data frame and try and see what you see in these matrices. If you're using GGPlot, I think last time we talked about GGAlley, which also does this. Is a library called GGAlley, which does GGpairs, which allows you to do pair by pair matrices, and it allows you to do a little more nuanced representations. You can choose what type of representation you want, whether you want a bar representation or you want some. So this is iris done in GGpairs, and you can see. Well, in this case, it's numeric versus numeric, so the 6 are common, but it's also given you in the middle a distribution for that variable. Kind of just plotting that variable itself and showing you the distribution. So GGpair or GGAlley, which is the library, allows you to do kind of use GGplot to do these pair by pair, and you can choose the type of distributions also. So it's kind of one up on it, but it's a little slower. So plot is faster, but obviously it doesn't allow you to choose. But GGpair allows you to choose, but is a little slower. And yeah, you should use it when you have maybe fewer variables to kind of look at. Alessandro, you want to add something?
Yeah. So I guess one of the things that I would add, just since we've got this right here in front of us, is that we can clearly see by looking at the diagonal that the four variables that we're looking at none of those are normally distributed. And in fact, the petal length and width have a bimodal distribution.
Right.
However, one of the things that we might expect is that if you were to separate the variables out to each species of iris, that you might actually see more of that normal distribution that you would expect. What you've got here is you've got three distributions that are kind of overlaid on top of each other. Right. So with sepal width, for example, it's very narrow. I think that's so a very narrow distribution because you've got it's very very tightly clustered and very and one overlaid on top of the other. I'm not sure if all of these would really be normally distributed without actually looking at them, but I could see that as being possible, and that would certainly be the case if we were to that would be the assumption that we would have if we were to do k-means clustering on this. K-means clustering basically has you look for normally distributed centroids of normally distributed numbers amongst a group of such clusters. So basically, if these variables are normally distributed within each class, k-means clustering should be able to find those means and exploit them to discover the clusters. If, however, the values are not normally distributed even within the clusters, k-means clustering will have some issues.
Sorry, just to stay on that. Multivariable visualization is saying, so the difference between GGPair, which you see there, is it's used color as a way of kind of showing the three clusters, right? So that's where we move to multivariable visualization. Is basically once you've exploited the two axes, you have to bring in something else to kind of now visualize, right? So one of the option is color. So color is a good way to kind of show the third variable. The other is shape. So you could have used a different shape, or you could have actually used size of the blob to show. So those are the three things you can actually use to kind of show the third variable just on the same chart. So color, size, and shape. And you can use GGPlot to experiment with how it'll kind of pan out when you have categorical variable and when you have quantitative variables. So it'll do some kind of shading in color, and it'll do some kind of sizing to kind of show that. And once you've exploited and you've kind of finished with using color, space, color, size, and shape, then you're left with now replicating the charts, right? So you kind of start faceting, which is basically saying, can I repeat the chart? So which is where you can repeat the same chart many times, which has become small multiples or facet grids or facet wraps to kind of show the same thing, because now you're finished with exploiting the color, size, and chart, and you're now repeating it, which kind of expands the space. So instead of one chart, you have many charts, but maybe smaller of them to fit it into the same size. So then that's how you get into faceting. And one ingenious way of faceting, which is not really faceting, but kind of is SPLOM, is kind of like matrices are another way of kind of showing the same data. So exploiting the space again to show the data. So after color, size, and shape, you have basically space to manipulate. And space can be manipulated as a facet grid or as a facet wrap or as a matrix, right? And once you've finished with now space also, then you need to find some way of layering, which is basically show one snapshot, then show another snapshot, then show another snapshot, which basically means you change the graph, which means you bring in interactivity. And one way of interactivity is if you have time dimension, you kind of move the time dimension and the graph changes, or it could be any other variable, and basically the graph changes as you change that variable, right? And that's basically interaction, because you've finished exploiting the static space that is there. So Just to think about multivariable is just to start from 2 axes, add color, size, shape. Once you're done with that, then think if you, or not done, if you want to, then say how you can use space differently. So wrap it or facet it or use matrices. And then when you're done with all that and you really want to add more variables or maybe see how the graph looks for different variable configurations, then you ask interactivity, which is basically trying to show different snapshots of the graph when you click on and move some of that, right? And that's kind of one way to think about multivariable visualization. You're just going up the hierarchy. You're basically saying how much of the page can I exploit and how can I exploit it in different ways to show the variables, right? And yeah, there are techniques around managing that. So how many variables can you show using color? Maybe not more than 5 or 6. Same for shapes, because you cannot distinguish. You should not use color and shape together too much because we cannot see so many differences. But color and size may work because the size of the bubble is typically easy to pick up. So there are some tricks and techniques, but just experimenting, going up this hierarchy would get you a good feel about how to go and do multivariable visualizations.
Something I might add about the interactivity is, if you're using R in plotting, as far as you're concerned, it's already interactive. You are interacting with the data. And really, when you have an interactive chart, all you're really doing is making it easier to do those things that you could do in R for other people. Right. So there's, if you want to make some, if you're putting something on the web that you want to share with, share with people that they can interact with, that's where having interactive graphics is really handy. But if you're just working, on something on your own, you just keep writing running the same plots with making little changes, and that's all the interactivity that you need. And if you're giving a presentation to somebody, you often really don't want them driving because then you don't know where it'll go. You want to make, you want to drive, and so again, just having, going digging deeper into the data with multiple charts and multiple plots that you might have on different slides is usually all that you need. I think
that brings a good point, Amran. There are charts you do for exploratory data analysis, which are really, you want to be able to generate many of them and experiment with lots of them and maybe use some of them, right? So you do 50 charts and then use only 1 or 2, right? And there are charts for communication, which should be different from the charts for exploration, or at least be more thought about, nuanced. And because then once you're communicating, you want to really say, okay, now I figured out these are the 3 variables that are important. I can decide how to represent them. I can then think about ensuring that the message is coming across in the visuals through those visualizations. I may need to do appropriate alpha clustering, whatever required to kind of communicate. And charts for exploration is where you can do R, and you may want some interactivity around it, but probably you can try with R itself. And R Studio has Manipulate as a library to kind of play around with one variable, or many other libraries like Shiny or GGViz, which is the next thing about GGPlot, to do that. But then when you come to interaction or when you come to communication, you may already have figured out what is the final view that you want to show and what is the level of interaction you want to build in for the final communication. And there the problem is fairly narrow, right? And then you can make some different choices around tools and representations than you would in the exploratory end, right? And I think that's kind of also one of the things to keep in mind. I think this is kind of a common confusion that I kind of see. When I go to some of these conferences and people come and present, they'll present the same stuff chart that they may have used to do the analysis. And when you're communicating to a large audience or you're communicating to a presenting, that same chart may not work that well, right? I mean, it may not be the one that understands that people may understand, or you may have to think about. So just put on a different hat. I call it different hat. Put on the exploratory hat and put on the communicative hat, and then make the choices around charts.
I remember. I think it was in an earlier office hours. You were talking about how you present your analysis, and you don't just narrate everything that you did. You tell the story about the data. You don't tell the story about yourself, right?
Yeah.
And I think the same thing is true in this case, where you really have to be, don't show everything. Show the data that tells the story that you're trying to tell. Don't just do a scatter plot of everything and hope that your audience will understand what it is that you're showing to them. You need to guide them, and you guide them with color, and you guide them with how you choose your scale, and you guide them with what you show and what you don't show, and what maybe if a variable doesn't matter for your story, don't include it in your chart.
Right. So I think that kind of is a question that I think you were telling also comes in the analytics side. So we're talking it on the visualization side, right? That is there, kind of a different theme when we talk about. Right now we're saying exploratory visualization and communication, right, or communicative visualization. Is there something similar like that when we talk about data analysis? And is there exploratory data analysis? And then when do we come to kind of the predictive part of it, right, or predictions? And those, even in analysis, we need to kind of think about two different hats, right? You may be actually exploring the data at some point, and there you may be doing different stuff, and then you may be actually trying to either do hypothesis testing or predictive analytics, and that's a different hat, right? And you want to talk about, because I think that's a question that comes in many of these one-to-ones.
Yeah. So. So first, if we go back in time, 100 years ago, when somebody would do an experiment, you go through a lot of trouble to define the experiment very carefully, make sure that you collect exactly the data that you need, and do your experiment with, before you even start the experiment, you know exactly what statistical test you're going to use, you know exactly what your dependent and independent variables are, and you just collect data and you perform the test. And that, is historically considered, the most honest way to do a statistical analysis. You go in with a hypothesis, you test your hypothesis. If you win, great. If you don't, back to the drawing board, start over.
Redo experiment.
But we have a situation now where we have tons of data, and we get the data before we come up with the hypotheses. Which is kind of backwards from a historical point of view. And this I think is fine, but it does require you to be careful, because what we find is that if you can just generate hypotheses from the data, it's very easy to find two numbers that correlate, or something that looks like it's an effect. And you're doing analyses that, in the old days when you had your hypothesis set out in the beginning would have been fine. But now you're finding, okay, well, I'm doing 20 tests, and, oh, this one has a p-value less than 0.05, so therefore I found something. Well, no, you haven't. You've just, that by sheer law of probability, if you run 20 tests, one of them will have a p-value less than 0.05. That's just probability. So what you need to do is basically, once you've done your exploration and you found something that looks like it might be worth looking into, you basically then do it again as if you were that old-time 19th century scientist collecting your data for the first time with a hypothesis in mind. Well, how do you do that since you've already got your data? Well, the way that you do that is when you first start out, you don't use all of your data. You actually only use part of it. And this is called cross-validation. So basically, you have a test-train split, and what train refers to as you're training a model. You're training a machine learning model, and the machine learning model might be linear regression. logistic regression, random forests, could be anything.
Mm-hmm.
Could be a lot of things. Maybe you're trying a bunch of different things on your training set, and you hit upon something that looks good. Then you apply that model or that to the test set and see if it still works. If it does, then that's a good indication that you've got something. So again, it's this trade-off between exploratory versus in this case confirmatory. But confirmatory would be the kind of the step before actually presenting something. You wouldn't want to present something that you had only gotten as far as exploratory on, because there's a good chance that you're wrong. And you don't want people to, you don't have to tell people, oh, I'm sorry, it turns out that was just noise. You want to make sure that you got it right before you start talking about it too loudly.
So you're basically trying to, in this train versus test, trying to create this kind of redo the experiment in kind of the confirmatory sense, right? You're using one part of the data to generate hypothesis, or not even generate hypothesis. In this case, just build a model that works on that data. But
I would call that building a hypothesis.
Okay.
I mean, each model is effectively a hypothesis.
Right. Right.
Each model says there's this relationship between these variables.
But how important is it important that you should be able? So this is one of the questions that I kind of stuck. I come from this old school, not in the 1900s, but even 10 years ago as a consultant.
You could have taken class yesterday, and they'd still be telling you that.
Yeah, but I was kind of like I call myself a small data guy, right? So small data guys build models, and those models would be kind of spreadsheet models, or models which are causal in nature, but maybe more small data driven. And so one of the questions I always have is this: you need to, in kind of the old style or kind of the classical statistical modeling, you need to build causal model, and you need to have a good causal explanation for why something's happening, right? In predictive, to some extent, if the model is working, you may not even want. Is it important to have a good explanation? Should you be able to tell that story, or is it good enough that kind of the thing works? How good of a story do you need after? So the model starts working now, and should you be able to tell why it's working, or is it okay because it's working? Like even it works with the test data. So.
Well, I'd say that there's sort of two schools of thought about this. I tend to be more of a traditionalist and say that you should be able to explain it. And the reason, but I know people who are, quite good in their field, machine learning experts who say, who will just throw the whole kitchen sink at their model and never look at the coefficients. They just, work. That's good. Now, machine learning practitioners of that ilk have to be very good at doing cross-validation, doing parameter searching, doing all kinds of automated methods to verify that their model is not bogus. Right. And even with all that, you can still miss it. So I definitely am a traditionalist in this regard. I think that it is good to look at the coefficients, to see that your model makes sense, that you can at least somehow come up with an explanation that maybe it isn't what you thought, and that's often the case. That's actually when it gets interesting, right? Is when you discover something that you wouldn't have occurred to you, but then in retrospect it's like, oh, of course, but right. You hadn't thought that before. If you can't, I think that's probably a good indication that you did something wrong. That you've got, I learned a new fallacy. Not really fallacy, but a new, what do you call it? It's sort of when you do something wrong. But there's maybe kind of an anti-pattern, but logically. That it's called time traveling, and what happens is you in building your training set, you manage to introduce some features that that kind of predict the outcome without meaning to. And so you've got information from that you're trying to predict creeping into your features.
Right.
And this is surprisingly easy to do completely by accident. Probably the sort of simplest example of this that I saw was somebody trying to predict the outcomes of basketball games, and they didn't notice that the data that they had would have the stats for team A and the stats for team B right next to each other, and so that was the data frame was basically had team A stats and then team B stats as columns going down.
Mm-hmm.
He failed to notice that team A always wins. That was just the way that the data was arranged. That they always put the team that won first, and then they put the team that lost second.
Right.
So this model kind of learned that the first team always wins. And doing his training set, it came out with 100% accuracy. And then as soon as he tried to do it on a testing set, it was 50-50 chance. And he was like, how can it be so perfect in one case and so wrong in the other? And that's, it's because there was information there about the way in which the features were set up that, if you're not paying attention, you can easily miss things like that. And there's ones that are way more, that's an easy one to explain. There are times that I've seen that happen when I've done it myself in ways that are very subtle and easy to get messed up by.
Yeah, I think even in kind of, I go back to my own spreadsheet modeling days, and even there you could come up with these. We used to have these complex spreadsheets where, at some point, our causal explanation would start to break down, and that's really where it's tricky, because when you don't know what the answer is, but the spreadsheet is giving you the answer, that's kind of like dangerous territory, because then you're just tweaking variables, and I can see where this kind of fits in.
I think that if you find a relationship and you say, well, that doesn't really, I can't understand that, and you dig into it and you still you can't explain it away, that it stands up to everything that you try to put against it. Well, maybe you've really discovered something that you just really, that's just really hard to explain. We live in a complex world, right?
But I guess along with curiosity, which we said is one of the things you also want to be skeptical a little bit, right? Mm-hmm. So skeptical when the results are too good to be true, and skeptical when nothing's making sense. I guess in both cases, and it probably makes sense. Okay, so any other questions? Just jump in. But if we've got another 14 minutes or so, and I was kind of thinking about, maybe one thing we can talk about is, we talked what, New Year for data science is, but, what do you see as kind of what happened in the last year, and is there in the data science area, right, that people should be aware of, and, and maybe even we'll see more of that this year. Like, so what are those kind of, 2 or 3 trends that were kind of that you felt as a data scientist coming into your work, and what do you see maybe even continuing this year, or even if there are new things that you're looking forward to? I think both of that would be good. So what did you see something interesting last year that you think we'll be seeing impact of even this year?
So I think the 2 things that really sort of struck me. One is so I'm something of a big data guy, so I've been excited to see that Spark has really taken off, and Nathan, who is a kind of a, I think he's now a Spark evangelist, but he kind of came around to that position over the last probably half year. He was commenting that you go to Strata Hadoop World in New York, and it's more about Spark than Hadoop now. Now, so what is Spark? Actually, hold on. I want to see this. You mentioned coefficients for prediction models. All right, let me finish my thought, and then I'll get to the question about coefficients on prediction models. Mm-hmm. So Spark Spark allows you to basically operate on big data in an interactive way. This makes it very different from Hadoop, which requires you to do everything as a batch job.
Okay.
The Hadoop MapReduce system, what it does, well, first of all, what MapReduce does is it allows you to distribute tasks across big data. It basically puts the work of the job at the site where the data is. This is very convenient when you're dealing with terabytes or petabytes of data, and trying to send that over the internet it's just not going to work.
Okay.
So you need to operate on it remotely and then have the results shipped back to you and kind of aggregated and coalesce.
Mm-hmm.
Problem with Hadoop is Hadoop does everything as a batch job. At every step, it reads and writes to disk, so it's very, very slow. And so you write a script to do something, and then go get a cup of coffee, and an hour later, if you're lucky, you have your results. That's the minimum amount of time.
This is a mainframe style processing, it sounds like.
Yeah, yeah, absolutely. It's like, imagine using R, and every time you hit return, you have to wait an hour.
Mm.
You can't work that way. Spark is really cool because it's actually it's actually built on top of the Hadoop distributed file system, so your old Hadoop stuff still works. But now you have this infrastructure where it does everything in memory. It loads the data that you're using into memory, so you can iterate very quickly, and you can work on it in an interactive way.
Okay.
So that's pretty exciting.
Right.
The other
Before
thing.
you go to the second one, huh? You want to pick that question? Yeah. Coefficients for prediction models.
So the coefficients about prediction models. Actually, so let me back up and say something about. I want to talk about exploratory versus predictive analytics, or
confirmatory versus predictive. Yeah.
Confirmatory, or what are some other words? Inferential statistics.
Inferential, yeah.
So inferential statistics. All right. Well, so exploratory analyses, basically you have a bunch of data, and you are looking for the shape of the data. You're looking for the shape of each individual variable. You're looking for the relationships between different variables. You might do a Splom plot to kind of see if there's what the relationship between different variables are, if it looks like there's a correlation or not. Or you might do some numerical analysis, like principal component analysis or clustering, to see if there's relationships.
Mm-hmm.
There's nothing in those cases. There's no single output exactly. You're just you're kind of just looking at, you're kind of taking this sort of data, hyperdimensional data cube, and rotating around, kind of getting a sense of what's going on.
Mm-hmm.
Inferential statistics is you take that, and that's your x, and then you have a y that you're trying to predict. And y is usually a single variable. There are some cases where it can be multiple variables, but for simplicity, we'll just talk about it being a single variable. And it can be a categorical variable, or it can be a continuous variable. So a categorical variable would be, a yes or no, like did they buy it or not buy it, or whatever. And a continuous variable would be, what you think it is. It would be the number of clicks or the number of whatever.
Right.
And what you're doing in inferential statistics or predictive analytics or any of the, those are all different words for basically the same thing, is finding a relationship between x and y, so that you can see how x changes with y, and how you can essentially predict y given x.
Mm-hmm.
And even there, you might actually do, when you're doing that, that might still be exploratory. And this comes down to, so what you end up with a lot of these methods, let's take linear regression, because that's the simplest example, is linear regression. You're taking each individual variable, each of the x variables, each of the,
independent.
And you're sorry?
Independent variables, I said, yeah.
Each of the independent variables, and giving it or finding a coefficient that measures its effect on your dependent variable, your y.
Mm-hmm.
So the coefficients show a relationship with linear regression. The coefficients are actually very straightforward. All it means is, if you have a coefficient of 2, that means that every time x goes up by 1, y goes up by 2. Mm-hmm. That's what that means. Mm-hmm. If your coefficient for x is 0.5, that means every time x goes up by 1, y goes up by 0.5. Mm-hmm. There are other ways in which that becomes more complicated, like when you do a logistic transform on it to turn it into a probability, but that's another topic for another time. So the coefficients, now the size of the coefficient doesn't necessarily indicate how strong the effect is or how robust the effect is. Mm-hmm. It could be that a variable only affects, that an x variable affects the y in a very small but very predictable way. It could be a very accurate predictor, whereas there could be another x that has maybe a very large coefficient, but it's wrong a lot of the time. So each coefficient will actually have, you can actually calculate basically do a statistical analysis on each coefficient to see if it is, if it has a statistically significant relationship to the outcome variable. Generally speaking, a larger coefficient will have a lower p-value, will indicate a stronger relationship, but it's not necessarily the fact.
So when you talk about coefficients, you're not talking about the coefficient in the model. You're basically saying look at the p-values or look at the other values to see how strong that variable is actually really in predicting. That's what
I would say both. I think that you want to, that the coefficient, the coefficient is telling you what the actual relationship is. The p-value is telling you how confident the model is that that coefficient is significant, or mm-hmm. is not a, is not noise, basically, sort of. Anyway, yeah, if you have if you do your analysis and you get back the p-values, and you've got a lot of variables that have a high p-value. Mm-hmm. Those variables, you can pretty much ignore them probably. They probably don't have much to do with your outcome. And so once you get rid of those, and this is what's called feature selection. Mm-hmm. So feature selection, it allows you to basically, you go through the features that you have, look at their influence on y according to the t-statistic or p-value, which are basically the same thing, and use that to kind of throw away the variables that you don't care about. Right. Then among the variables that you do care about, you do want to look at those coefficients, because it's not just a matter of is it significant, but also is it significant in the way that you would expect it to be significant. Because I've had cases where I've seen a negative coefficient where I expected to see a positive one, or vice versa, and that's that raises a flag just as much as a p-value being 0 or 1.
I think we should come back next time to this, because I think this kind of what you guys call the machine learning pipeline, or this whole way of kind of thinking about, it's modeling in kind of the predictive world is not just about running and throwing libraries at it. It's to some extent figuring out what feature selection you would do, right? Or which variables to keep, which variables to throw out, and then build a simpler or a more predictive model out of that. I think that is one topic that we should probably pick up next week and elaborate a little bit, because that's something that's very different from what you would do in conventional stats, right? Because there, as you said, with limited data, you're far more hesitant to throw out any variables, and you want a model that is more causal, and you're trying to look at something. Here you're trying to just say, which are the minimum number of variables I need to kind of predict the outcome, right? And how can I build that model? So I want to learn a little more about feature selection, and maybe we'll kind of pick that up next time and talk about this, or next time when you're back, about
oh, that's right. Yes, I will not be. I think Gabriella will be taking my place, mm-hmm. And then I'll be back the week after that.
Okay, so we're looking forward to kind of a one-page, one diagram that we can use to anchor a talk on feature selection and machine learning, and then how do you go to prediction, right? That's something like I think we can kind of iterate and see if we can use that to kind of talk about this, and maybe a simple example that we can use to do that. Maybe how we would do that on the iris case. I don't know whether that makes sense. Out of the 4, would you use 1 or 2? I don't know. Maybe that could be one.
Use one variables in that, but
yeah, that's probably got not too many variables.
You can, of course, we can amplify the number of variables by adding in polynomials and interactions. So we can get as many variables as we want. If we want to do that.
Good. So I think before we end, because we're going to end in a minute or two, just a couple of more thoughts, because you kind of started on that Spark. So one more thing that you were talking about that people should be ready to learn. Jupyter. And yeah, Jupyter as not the planet, but Jupyter as the
planet. This is so the IPython notebook project originally came out of IPython, which obviously is it's short for interactive Python.
Mm-hmm.
And it's really gotten a lot of steam, and a lot of people started using it to develop Julia notebooks and R notebooks, and
right.
And people started developing ways in which you could shuttle data back and forth between these different languages very easily within the notebook. And so what's happened is in the new version of IPython notebook that's coming out this month, is it's actually no longer IPython notebook. It's now Jupyter, and Jupyter stands for Julia Python R.
Wow. Okay.
And so the idea, so they're really kind of hinging their wagon to these 3 languages, Julia, Python, and R. Everybody obviously knows R, and I'm sure all of you have heard of Python if you haven't used it very much yet. Julia is less well known, but it's kind of exciting. It's still very new, but it's a language that's I'm doing math, and it's very easy to use, and it's incredibly fast. So a lot of times, if you are doing something that just takes too long in R, you might want to try redoing it in Julia. Full disclosure, I've never actually done that, but I hear that it's very easy to use.
And the idea of Jupyter is, if you guys have used R Markdown, it's kind of builds on that, right? It's kind of literate programming, right? That you not only write the code, but you also explain the code, why you've chosen what to do, and you kind of see the output as you write. And everybody who wants to become a good data scientist needs to be doing more literate programming, right? Not just writing programs that you only understand, but be programs that other people can reuse. And I think that's where start using R Markdown and start looking at Jupyter as a way of thinking. So I want to add just one more thing to that kind of theme, more from the visualization ad. If you guys are interested in looking at visualization, I think the trend to look at is obviously interactive, things that kind of allow us to do more. So on the R space, keep an eye out for GGViz, which allows you to do, which is the next level of GGPlot. If you're doing on the web and doing statistical visualizations and you want to use R or Python, there's a good site called Plotly. And Plotly allows you to do a lot of those, use these languages interchangeably and do a lot of the scientific or data scientist kind of things and actually share it. So you should try out Plotly. But just keep an eye out for interactive visualization. I think that's where, at least even in the stats part, even in the exploratory part, there is going to be lots more development. And if you want to go onto the web, then the domain is endless. D3 is the one to kind of look out for, or it's kind of gaining steam. So yeah, so for me, I think it's basically trying to think beyond, escaping the flatland, as I call it, like moving beyond a flat space and look out for interactive. So Spark, Jupyter, and maybe GGViz. Yeah, 3 things to kind of look out for in the coming years. Well, good new year, start to the new year, Alessandro. I think, and we've got at least one topic that we will pick up when you come back on machine learning, or explaining the machine learning pipeline, as I understand it, or as I don't understand it, and I would like to understand it. And yeah, and I think it's great to have people join us. So thanks, Adam, Santosh, Gustin, and I think these questions help because Alessandro and I can talk and we can keep talking about lots of stuff. But when you ask some questions, it forces us to kind of think and maybe answer some of the questions that are actually more helpful directly to some of your challenges. So just keep asking these questions in live or actually even before, or just shoot across those questions to us on the forums. And yeah, let's keep doing this. This sounds fun.
Nice.
Good. So take care till next week. Thank you, everyone.
Well,
Bye.
till 2 weeks from you.
Bye. 2 weeks. Yeah. Bye.